Welcome to this lecture on buffer design considering inverse narrow width effect. So, this is a part of module 2. So, in this lecture we will discuss buffer design and how to reduce the energy consumption per cycle while designing the buffer within a certain constraint of delay. So, and here we will use inverse narrow width effect. So, the buffer would is chain of inverters which drives a large load. It could be an interconnect load, an IO pad. So, let us call it CL, and we have a input capacitance. So, input capacitance is specification and also the load capacitance is a specification. So, in this we are now going to use all the work that we did for effective current of a near threshold inverter. So, what is the delay of an inverter here? So, if we have a scenario where the input and output transition times are equal, the inverter is balanced, a balanced inverter is designed, that we have discussed in the previous lectures, how to design a balanced inverter in near threshold voltage regime. So, we have a balanced inverter now, and in that balanced inverter the input and output transition times are always maintained equal, suppose. So, you have this chain of inverters is sized such that for one of the inverters, say this inverter, the input and output transition times are equal. This is the device under test. So, this case what you find is that when you plot delay of the inverter, versus the output capacitance by its own input capacitance. Okay. So, here you have C out, output capacitance, and input capacitance. Let us differentiate this by calling this Cn1, input capacitance of the first stage. Okay. So, if you plot this and you keep on increasing, you will find that this is along a straight line. So, what is this straight line? This, as we had discussed in our previous lectures, this straight line would be the delay D would be given by C out by C in into VDD by 2I effective. So, this is nothing but C out VDD by 2I effective, that is what I am writing in this way, plus whatever is the parasitic capacitance by Ci effective, parasitic capacitance of the inverter into VDD by 2, because we are dealing with 50% delay, that is why this a factor of 2 in the denominator appears. Now, we know that the parasitic capacitance and the effective current are both proportional to width. So, therefore, this would turn out to be a value delta into H plus a parasitic delay. So, if we also write C in, so in that case Cp by C in, suppose it is to delta. So, where we can now see that H is C out by C in for the inverter design under test and P is Cp by C in. So, as we know, Cp would be proportional to the parasitic capacitance would be proportional to the width of the or the size of the inverter, and C in would be also proportional to the size of the inverter. Okay. Suppose for a template inverter, we are saying that the NMOS, so this is the device under test and the parasitic capacitance is shown as Cp. So, as we had seen earlier in this course, Cp would be proportional to the size of the inverter and input capacitance also is proportional to the size of the inverter. Therefore, this factor, this term would be a constant if a given layout discipline is followed, as we will discuss later. So, what is this delta? So, that is C in VDD by 2I effective. Okay. So, for the entire inverter chain, suppose it has a number of stages n, a fixed number of stages. Then for the entire inverter chain, we would find that the delay is capital D, which is the delay of each of the inverters added. So, you will have delta common into H1 plus H2 plus Hn, okay, all the this electrical effort, this we call electrical effort, this we call intrinsic delay and this we call parasitic delay. So, all these electrical efforts added plus all the parasitic delay is added. So, if since parasitic delay is independent of the width of the device, you will have just n into p, because n number of stages are there. Now, you want to minimize this. So, as we know, when you multiply all these h1, h2, hn, you get a constant C out by C in. So, when the product is constant and you want to minimize the sum, you would say that when the product is constant and you want to minimize the sum, you would keep all the terms equal. So, therefore, all these terms should be equal for minimum value of D. So, what does that mean? That means that all these H is equal to, you can call it, all of them are equal and they are H, and that is C out by C in to the power 1 by capital N. This is for a fixed number of stages n. Suppose now I want to also optimize n for minimizing delay. Now, I have a problem. When I change the finger width of the inverter, because of inverse narrow width effect, the effective current of the inverter changes. So, and also the leakage currents of the inverters changes. So, suppose our specifications are that you are given a maximum delay constraint and you want to minimize E total equal to E dynamic plus E leakage while meeting the maximum delay constraint. Suppose this is the requirement. So, this leakage energy would depend on the finger width of the, because with finger width we know that due to inverse narrow width effect, the leakage current changes and the effective current also changes. Therefore, delay D would also depend on the finger width of the device. So, layout, number of fingers, finger width of the devices, that they would determine both the leakage current as well as the delay. So, both of these are now affected by, both are a function of inverse narrow width effect and or finger width of the devices. Now, so how do we minimize? So, when you reduce the finger width of the device, the threshold voltage of devices reduces. So, when you reduce finger width of the device, if you reduce the finger width of the device, finger width, so this reduces delay of the inverter, increases I leakage of the inverter. So, you do not know whether the leakage energy reduces or increases, delay reduces. Okay. So, as you keep on reducing the finger width of the devices, the leakage energy would keep increasing and delay would keep reducing. So, there would be an optimum with respect to the finger width of the device also. So, how to consider this in buffer design? This is the quest that we are now going to answer. So, we would also like to find the optimum value of finger width of each of these devices, which gives rise to minimum energy consumption for a given delay constraint. How would we go about doing this? So, we want to minimize the delay as well as minimize the leakage consumption. So, or total energy consumption. So, one thing is that for the layout to be simple, you require the number of fingers of N MOSFET and P MOSFET to be equal. So, for that we had discussed in the previous lecture that how would we fix the values of the number of fingers of N MOSFET and P MOSFET and finger width of the N MOSFET and P MOSFET for equal rise and fall times, that is for a balanced inverter. So, we first obtain balanced inverter with now finger width of P MOSFET WPF, finger width of N MOSFET WNF and number of fingers of NF, which is equal for the P MOSFET and N MOSFET. Okay. So, and we are dealing with near threshold voltage operation. So, once we obtain this, so now we fix this number of finger width constant for all the inverters in the buffer. Okay. So, what is the total delay. So, as we have seen, for a given number of stages, for a fixed number of stages, the delay would get minimized when the electrical effort H of the case stage k, the electrical effort of the stage k is equal for all the stages. That is, for a given n, all the values of these electrical efforts should be equal, that we have seen earlier for all the k. Okay. So, therefore, we could write this delay as if h to the power 1 by n into n plus n into p inverter. Now, we know that this p inverter is a function of number of fingers, that we will take into consideration later. Now, for a given number of stages, this relation is valid. So, this will minimize the delay when you have the electrical effort of each stage to be capital H to the power 1 by n. Now, for what if you want to minimize the delay by optimizing n number of stages? Why is this possible? Let us see. So, when you increase n, number of stages increases and H, the electrical effort of each stage reduces. This increases delay, this reduces delay. So, minimum delay for what value of n? So, we do not know this, that is, for what value of number of stages does the delay minimize. So, that is something which needs an optimization. So, here you would say that you want to minimize delay. So, you want to minimize this. So, that would be plus n into, we could have written it this way. Now, this is h to the power 1 by n plus n into h to the power 1 by n into minus 1 by n square natural logarithm of h plus p inverter. So, this becomes 1 by n minus h to the power 1 by n into natural logarithm of h to the power 1 by n. Okay. So, you could have written this as h to the power 1 by n into 1 minus. Here, as we had already discussed, this is a function of number of fingers. So, our method would be that first fix the number of fingers, obtain a balanced inverter, as we have said. So, first obtain a balanced inverter for a given number of fingers. Minimize the delay by fitting into this expression. So, by changing the number of stages n and fitting this so that this expression is valid. So, obtain the P inverter for that finger width of the inverter. So, how will you do that? You will have a layout where you maintain that finger width of the inverter. Okay. Suppose this is n MOSFET, it is just a kind of concept diagram, it is not the real to the scale kind of picture and it is just indicative. So, this is the width of the finger for P MOSFET, this is the width of the finger for N MOSFET and here number of fingers is 2. So, if you, so here you have the drain of these two devices. Okay. This is source. So, with this arrangement have 6 number of fingers 6. So, keep number of fingers to be 6. So, that is fairly value of number of fingers which would give you an average kind of value of drain capacitance. So, with this number of fingers plot the delay of the inverter versus load capacitance C out by C in of the inverter, okay, delay versus C out by C in of the inverter. So, from that obtain the P inverter for this. So, doing this we obtain the P inverter for this number of fingers. Okay. So, first we have a number of fingers fixed and for obtaining balanced inverter, as we have discussed in the previous lectures, we will obtain a value of finger width of the P MOSFET which balances the inverter. Okay. So, with that finger width of P MOSFET and number of fingers, we will obtain the through the delay for about number of fingers 6, we will obtain delay versus C out by C in. That would give us the P inverter, parasitic delay of the inverter for that number of fingers. For that, now you fit, now use this parasitic delay of the inverter, which is a function of number of fingers. So, you will now correct this, you will now further refine this. We will say that this is h to the power 1 by n to 1 minus natural logarithm of h to the power 1 by n plus P inverter, which is a function of number of fingers. P inverter is now a function of number of fingers. So, you optimize the value of n. It is found that for typical values of P inverter, this actually fits on a straight line and the delay can be given by this. So, it actually fits on a straight line. This expression fits on a straight line. So, we obtain the delay of the inverter using this. So, this is in the units of delta, all this is in the units of delta. So, we should observe that this is in units of delta. Okay. Now, how do we obtain the best value of number of fingers? How do we obtain this? This we will discuss next. So, what have we done? For a given number of fingers, we have obtained the value of WPF, finger width of P MOSFET, which would give a balanced inverter. Now, for that number of fingers, we have obtained the optimum value of n. So, this expression, so we need to optimize the value of n or get a value of n number of stages, which would fit on this expression for this number of fingers, for a given number of fingers. Okay. That is for a given, in fact, I would say for a given WPF and WF. So, it is found that this expression actually fits on a simple linear expression when the range of interest of P inverter is seen. So, the range of inverter of P inverter is around 1, say it cannot be smaller than 0.5 ever. So, it is 0.5 to say 1.52 like that. So, in that within that range, this expression can be approximated by this linear expression to a very high level of accuracy. So, till now we have what we have done is we have an optimum number of stages for a given value of WNF. So, now we want to get the best value of WNF. So, how would we get that? So, we will follow an iterative method. In step 2, we reduce the value of finger width of the N MOSFET. Okay. That would lead us to increase the number of fingers, adjust the finger width of the P MOSFET to balance the inverter. Okay. And now we obtain P inverter of this number of fingers. Okay. And then we obtain optimum value of h to the power 1 by n, which we call rho, and that we obtain as 0.71 into P inverter of this finger width of N MOSFET. So, corresponding finger width of P MOSFET also, okay, plus 0.73. So, that gives us this rho inverter, okay, rho of this number of fingers or rho of this finger width of the N MOSFET. So, now we have capital H, natural logarithm of capital H divided by natural logarithm of our rho this gives us the optimum number of stages, and this optimum number of stages may not be integral. So, increase n, let us call this n optimum to the nearest integer on the higher side. Okay. Why on the higher side? Refer the book Logical Effort by Sutherland, Sproul and Harris. In fact, the full name of the book is CMOS circuits. So, now you have obtained optimum number of stages. Okay. Now, we discuss the delay. We know the E leakage per width of that device of the inverter. Okay. We can calculate I leakage, average I leakage of the P MOSFET and N MOSFET. So, E leakage we estimate as average I leakage into VDD into the delay of the buffer. So, delay of the buffer gives us a fair idea, assuming that delay of the buffer is the time for which you need to keep in proportion to the delay of the buffer, you need to keep the circuit in an operating condition. Otherwise, you can put off power gate, whatever the circuit. So, that is why total delay of the buffer good measure to calculate the energy, otherwise you get leakage power. So, now you have E total is equal to total capacitance of all the stages into VDD square, which is dynamic energy, total dynamic energy of the buffer, because each of the stage would have switched once in the entire cycle. So, therefore, this is the total dynamic energy of the buffer plus I leakage, the average value of P MOSFET and N MOSFET into VDD into total delay of the buffer. This is the total energy. Now, this total energy you calculate. Okay. Now, in third step, repeat step 2, repeat step 2, okay, that is reduce NF, reduce the width of the finger width of the N MOSFET, that is increase number of fingers, therefore, adjust the value of the finger width of the P MOSFET so that the inverter is now balanced, obtain the value of parasitic delay of inverter for these values of WNF and WPF, obtain the optimum number of stages, for those optimum number of stages, obtain the value of total delay of the buffer. Once you have total delay of the buffer, calculate the total energy. Okay. If this total energy still reduces, if it reduces compared to the previous value of WNF, if E total reduces, okay, repeat step 2, else use the value of WNF, WPF and WNF and WPF. So, use this value of inverter, number of finger widths and design the buffer. So, what is the procedure that we are using? That for a given load capacitance and input capacitance constraint given, we first fix the number of finger width of the N MOSFET, get a corresponding finger width of P MOSFET which would balance the inverter. Using that, these values of finger width of N MOSFET and P MOSFET, we use the traditional logical effort method and optimize the number of stages. Then we reduce the finger width of the N MOSFET and thereby readjust the finger width of the P MOSFET, obtain, again use the traditional logical effort method as I have described and obtain the total energy. This total energy, if it is reducing, go for the second value of the latest value of finger width of N MOSFET and P MOSFET, else go for the previous value of the finger width of N MOSFET and P MOSFET. This would give us minimum energy possible and while also minimizing the delay. So, thank you.